How do I do that every time? Okay, so any questions on the steps where your boss gives you a number for gain, R in or R out? You do small signal analysis to find an equation for gain, R in or R out. And then you set the number that your boss gave you equal to the equation that you found doing small signal analysis. And then you solve for the unknowns in the equation. So is that pretty good? Okay, and of that, of those steps, first of all, getting used to using those steps is kind of tough. I know Bron has what's Bron's thing? Those initials where you
Mohat.
Mohat, yes. He has Mohat. These don't really have. I'll try to come up with something interesting, but yeah, these 3 steps are the design steps. Get the specs, find an equation for the values your boss gave you, set them equal, and solve for the unknowns. And then you actually, once you solve for the unknowns, now you can actually build the circuit. You can find resistor sizes and all that. Resistor and capacitor sizes. Okay, so those 3 steps, getting used to them is a challenge, but there's the thing that takes the most getting used to is going through the small signal analysis to come up with these equations for gain, Rn, Rout, or GM. So what I'd like to do is I'm going to give you kind of a multi-step design problem. So that's for this. Now we're going to use a different circuit here. So again, my pen's going in and out, so let's see if it's working now. It is, cool. So what kind of amplifier is that? What's that?
Common emitter.
It looks almost exactly like a common emitter and common base. And you're
sorry for cutting you off, my bad.
If you look at a common emitter, it looks exactly the same, except in the common emitter case, V ins on the base, and there's a DC voltage on the emitter. Whereas for the common base, you have a DC voltage on the base and the inputs on the emitter. So just the emitter and the base get flipped. Okay, so let's see what happens here with the common emitter. If I raise V in, what happens to the current through the transistor? What do you think?
Increases.
Increases, so it goes up. And if the current goes up, what happens to V out?
It goes down.
Goes down. So if V in goes up, V out goes down. So is this inverting or non-inverting?
Inverting.
Inverting. So the input and the output are going opposite directions. So it's inverting. Let's see what happens over here. Let's say V in goes up, just like we did over here. What happens to the current? What happens to the current?
Goes down.
Goes down. Why is that?
VBE decreases.
VBE decreases. So this goes down. So here's VBE, and the current goes down. And so what happens to V out?
It increases.
It goes up. Goes up. So now V in goes up and V out goes up. Hey, they went in the same direction. So is this inverting or non-inverting?
Non-inverting.
Non-inverting. So that's one of the big differences. There's non-inverting. And this is inverting. And another thing is that, let's look just at V in here. If I, on the common emitter side, if I change V in, does this current change a lot or very much?
Yeah, it changes. Oh, wait, sorry. I was thinking of IC.
Yeah, it's not IC, that's the trick. This is IB, so whatever IC changes, it gets divided by beta. So this actually doesn't change very much. So if you change the voltage and the current doesn't change very much, is that looking like a big resistor or a small resistor?
Big resistor?
Big resistor. So this looks like a big Rn, just from looking at it. What about over here? If I change V in, does the current change a lot or a little?
A lot.
A lot. So if you're sitting here and you say, oh, I changed this voltage, oh, the current changed a lot, does that look like a big resistor or small resistor to you?
Small resistor.
Small resistor. So this has a very small Rn. This has a big Rn. So is a small Rn good?
No.
Generally not. If it's a voltage amplifier, you want a big resistance on the input. You don't want it stealing current. But it turns out for a common base, there's really only one place you use it, and that's when you have to impedance match. So let's see. Does anybody remember the maximum power transfer theorem?
C squared over 4R Thevenin.
Okay, how about just like a, so the separate from the math, how do you get the maximum power transfer? Because actually I don't remember the math, so you're probably right.
Is it the complex conjugate of the, oh, no, I might be thinking of the wrong thing.
It is, but in this case, let's just think resistor-wise. So,
isn't it when your
equal
resistor matches, your load resistor matches your internal resistor?
yes. So the common base is often used when there's some impedance match that you have to do, some kind of wire or transmission line, or most commonly, if you have an antenna, that's supposed to be an antenna. If you want to make an amplifier that's connected to your antenna, you'd like to match impedance so you get the max power off your antenna, and that's a place where you often see a common base. And if you've seen it drawn in books like this, it's often drawn sideways like this so it can connect to an antenna. But it's hard to see this way, so if you rotate it down, it just looks like a common emitter with the DC voltage and the input switched from the base and the emitter. Okay. So I could have written this like this. But that looks weird to antenna people. But it's easier to see that it's just really the common emitter. You're still changing VBE when you change VN.
Tina, do you mean common base?
What did I say? This is common base. Did I say common emitter?
Yeah.
Okay, sorry. Thank you. All corrections happily welcomed. Yeah. Okay, so and we'll look at that in a little while, but my first question to you is, so I'm going to have to set up groups again. I'm sorry it takes so long every time. But my first question is question one is, if you're going to use this as an amplifying stage of whatever amplifier you're building, you need to know the gain. And this is where it seems like it should be really easy. You know, with a common emitter, you could just directly find V out over V in, but this is one of the circuits where you have to find GM and you have to find R out separately and multiply the two to get your AV. So your first challenge here is for, I'll redraw the circuit here just to make it really clear. We'll call this R. Your first challenge is to, let's just do one at a time. So go in and when I set up these rooms, I should already be setting them up. Oh, wow. It kind of, oh, I see what happened. Okay. Your first job as a group, I am sharing, right? Is to find GM. So give me, I'm sorry yet again, give me 2 or 3 minutes here to set up your rooms.
Could you go back to the screen share? I didn't have time to write that down.
Okay, just a second. Let me move this over here so I can, that disappears. How about this? Okay. Okay. Oops, nobody else in that room today. Whoops, there's 2 Nathans. Okay. Jeez Louise. Two is here. Not here. I'll come back. I'll call y'all back in 5 minutes. Oh my God. Were you all able to get it?
I was still having some trouble.
Okay, let's go step by step. That's why these are, you know, more practice you do, the easier they get. So this is all just practice, and hopefully, you know, in your group you have people to talk to. So if you get stuck, you can get some help. But let's see, we've got 28, so we're still missing a few people. Got a couple there. Got that room. Okay. Come on back, y'all.
Tina, quick question.
Uh-huh.
I know that we ground the VDD because we ground all DC sources. We should also ground VB, right?
Exactly.
Okay.
Didn't have to do that with the common emitter because the DC terminal. So again, common base and common emitter, they both work by changing VBE. One changes it by changing the base voltage. One changes it by changing the emitter voltage. We didn't have to ground the common emitter because that was already a real ground. But if we had, for example, in lab right now, you're using like -5 volts to +5 volts. -5 volts, that would be grounded. Okay. Whoops, still have a room. Let's give it one more try. Come on back. What's a good thing to tell them to do? Hop on. Hey, y'all. How long does the message appear when you're in the breakout room?
Like 5 to 10 seconds or so.
Okay. Okay. So we'll leave them there. Okay. So the
Professor,
uh-huh.
I have a question real quick.
Okay.
When you're trying to find the sign of I out, in terms of like whether it's negative or positive,
Mhm.
is it the like, should you generally see it being positive when it's going towards the emitter, like the direction of going towards the emitter, or is it like relative to whether it's a common base or common emitter or common collector?
It depends more on this right here.
Okay.
So for GM, it uses I out. So it's the current. So if we're doing GM, what's the simplification you get to do with the 2-port rule?
V out is 0.
V out is 0. So let's do that. So V out is 0. And now for GM, this is taken as the positive direction.
Okay, that's okay.
That gets confusing with R out because let's say somebody gave you a resistor and they asked you, put this in a black box, and they said, okay, figure out how big the resistor is in here. You'd put a voltage on here and you'd watch the current going into the resistor.
Okay, yeah, I was just making sure. Thank you. That helps.
Yeah, so when you're trying to find R out, it's actually positive going into the circuit, but for GM, it's coming out of the circuit.
Okay. And then one more question. In all of our analysis, is it safe to assume, like throughout, like when we're doing this small signal analysis, that R pi and R zero in parallel with like the equivalent resistor GM will always simplify out to 1 over GM?
Yes, but I will hopefully, we're not going to have time. There's the next example I'll do in class, it looks like it's going to be Monday. That's a really messy one. And in that one, if you start simplifying down, doing those simplifications too early, you get an answer that doesn't work. So you generally want to keep them for as long as you can. And then at the very end say, oh, it's 1 over GM in parallel with RO. That's 1 over GM.
Okay.
But try to keep stuff all the way through till you're pretty close to the end and can see if it's going to do damage or not to do the simplification.
Okay, sounds good. Thank you.
Okay, so we did the 2-port rule here, and we've drawn in I out. And what I like to do is if I'm trying to find big GM, I look at its equation, and it's the equation for GM is I out over V in. And I find that KCL works best for me. So I look for a current in this equation here, and V in is a voltage. So I say, okay, let's make an equation for I out. So that is where I'd start making my equations. It's never clear just looking at the circuit where to start, but that seems to work well for me. If there's a current in the equation of the thing I'm trying to find, whether it's R out or R in or GM, taking that current and setting that up as an equation, that's usually a helpful, a good place to start. So let's see, what did people get for, actually, let's see if there's anything to simplify. That's always the next step. Is there anything you saw that you could get rid of, or?
R pi and R out are in.
Sorted out.
Okay, so that's something to be careful of. Is RO and R in parallel?
No.
No, I agree that they both are coming from this node, but R goes from this node to ground. And what about RO? It goes from this node, but does it go to ground on the other side?
No.
No, it's going to VN, and VN is not 0. So you can't put these two in parallel, but what was the other simplification you saw?
Collector resistor is shorted out.
The collector resistor is shorted out. So when you're doing the small signal analysis to find GM, you zero the V out. So this node is 0, but the other side of R is also 0. So there's 0 on both sides of this resistor, so it just goes away. No current goes through it, so you can just get rid of it. Okay, so then back to I out. What did you get for your I out equation?
V in times, or V in over, I guess, 1 over GM in parallel with R pi, but that could be.
Okay, you're right. I didn't have this grounded over here. Yes, okay.
Applied to V in times GM.
Okay. So, shoot, we didn't do the other simplification. You're right. So what do you see about the voltage across your current source? Good way to see if you can turn this current source into a resistor is you look at the collector voltage and you look at the base voltage and see if they're the same. Are they the same?
Yes.
Yes. So the voltage VBE is the same as the voltage CE. So that means this can go to a, I missed all of these shortcuts in my prep for class. Glad you're here. Okay, and then your R pi is over here. We'll leave it in. And this is your V in, and then you have your I out. Okay, so once again, let me get rid of that. And what's your I out?
It's a V in over all of those resistors in parallel.
Over GM parallel RO. Okay, and then for GM, it's actually I out over V in. So you have I out over V in equals 1 over GM RO. And why did I get something different? Let's make sure. Oh no, that's what I got. And if you work this out, what you should end up with is GM plus 1 over RO. And now you've gotten to the end and you have this equation and you see 1 over RO. What's 1 over RO approximately?
A really small number.
Really small number. So if you wanted to approximate this, then you'd go on and say
GM.
GM. Okay, so we've got our GM. The steps here we're going through today is to find gain. So what's the next thing you have to find gain? You've got your GM now.
R out.
R out. So I'm gonna go ahead and go back to your rooms and take 5 minutes and see if you can find the R out for this.
Quick question. Isn't R pi in parallel with 1 over GM and RO2?
But the current that you're interested in is this current.
Oh, yeah, that's right.
And this is going out this way. It's not going out the output, so you get to ignore it.
Okay.
Oh, Professor, I'm kind of confused at that statement because they're both ground. So are they not the same? Like you said, it's going out the other way, but that just goes to ground. So I thought I think it was Aaron, was right. I thought they were all in parallel.
Okay. Well, this is IB here. If you think of it, this is IB. This current, if you look back at, I'm not sure if this is going to confuse or help, but this current is actually kind of this current going this way or this way out the base, whereas you're looking at kind of this current. So it's two separate currents here. You're right, this is going to ground, but it's not going to the out. It's not going to this node.
Okay, interesting. Okay, thank you.
All right, so 5 minutes to find R out, big R out of your common base.
Professor, how do we join the breakout room again? Because I don't see the.
Did it disappear?
For me,
People
at
are
least.
disappearing. Let's see. Did you? Oh, I see. Which room were you in?
I think it was 5.
Okay.
Thank you.
Do you want to go to a bigger room? Or are you good with 2 people?
Sure.
Okay.
I don't mind anything.
You what?
I don't mind anything.
Okay. What about you, Joshua? Do you want to go to a bigger room or stay? I'll go throw you in a big.
Left for a little bit. But
Okay. I'll go throw you in a big room.
Okay.
Okay. Are you here for, that's the one, you're here for the next section? Okay. Did y'all get it?
I think I did.
Okay. It should look familiar.
Yeah, it looks very familiar.
Okay. You're the, oh, 2 people are back. I still haven't found that paper. I had like 16 things on my to-do list yesterday. I got 2 done.
No, no problem. I just remembered right now, actually. I was like, oh, yeah.
What do you want to do for your senior project, or what direction?
I have no idea right now, to be honest. I'm not even sure what I like, you know?
Yeah.
I mean, I enjoyed 307 and 308. I also enjoyed 329 right now. So the class I really enjoyed was digital design. Like, I probably liked that one the most out of all my classes. But it
133.
could also be that was like my first quarter here, so it was like, you know, that on top of everything else, maybe. I don't know.
Let's see. Here comes everybody. Okay. There's one holdout room again. But I'll start talking. Since I'm recording today, yay, I'll just start talking. Okay, so finding gain. Again, it's often easier to find GM and R out and multiply the 2 because you get to do a 2-port simplification. What's the 2-port simplification for R out? What do you get to do to your circuit?
Ground V in.
Ground V in. So we can do that. Do blue here. So after you do that, whatever you can get rid of, you want to get rid of it. So do you see anything you can get rid of here?
I don't think you're
Professor, are
sharing.
you sharing your screen?
Oh, I'm not sharing the screen. Thank you. Okay. Got our simplification, 2-port rule simplification to find R out. Base is already grounded because that's a DC input. Okay, if you ground V in, is there anything you can simplify here? Get rid of?
You can get rid of our pi, right?
R pi. So R pi goes away. There's a ground on both sides. Can you get rid of anything else?
You can put RO in parallel with R, big R.
Okay, so you can move that down there. You see anything else you can get rid of?
Your current source, right?
Yes. And why can you get rid of your current source?
Because Vn equals 0.
Yeah, VB equals 0.
VB.
So I always draw in VBE just because if R pi gets put in parallel with something, I lose track of where VBE is and then I make mistakes. Okay. So you have that. Whoops, could have drawn this better. So then you have V out. And even though this is pretty trivial, most of the R outs we've seen have been pretty trivial, but we're going to get to some harder R outs. So the way that you would do this kind of step by step is first identify your current. And remember, for resistances, you look at the current in. So it's the opposite of I out. I out goes out of the circuit. I test for resistance goes into the circuit. So to do that, I know R out is V out over I test, but I know V equals IR, so I could do I test times, now I see RO parallel R, but I want V out over I test. Is your RO parallel with R. So that's why in your last homework, when you did the .tf, you got almost exactly the same R out for the common base as you did for the common emitter. Okay, our ultimate goal here, now that we have big GM equals little gm, and R out equals RO parallel R. So what's gain? This has 1 plus 1 over RO, but
The product of the two.
the product of the two. So you get pretty much GM RO parallel R, which is looks a lot like the common emitter. What's different about this than the common emitter? So if you go back up here, oops. What was one of the differences between the common base and the common emitter?
This is in non-inverting.
Non-inverting. So you get, instead of minus GM RO parallel with R, you get GM times RO parallel with R. So this is this positive sign here tells you that this amplifier is non-inverting.
Professor, why do we call it I test when it comes to resistors instead of I out?
You just have to give it some name because it's not I out anymore. Since I out is defined as out of the circuit.
I see.
But for resistors, if somebody asks you, I'm going to get rid of this just to not confuse people when I post it. When you're looking at a resistor, if somebody gave you a black box, you'd watch the voltage at this node and maybe put some current into it. But the direction of the current to find a resistance is usually into the resistor.
Okay.
So here, when we're trying to find R out, we look at a current going in. I'll just use the pen if it's working. It's just, since I out's going the other direction, I just gave it a different name.
Okay.
It's just minus I out, though.
Right.
Okay. See, any questions? Okay. Next time we'll do a messy one to start off the hour.
Professor?
Yes.
So, in the case of both this and the common emitter, we're essentially trading R out for gain, depending on what resistance we have at the emitter, or at the,
Yes.
sorry, the collector.
Yes.
Okay. Is there like a generally optimal range that people use to get the best of both worlds?
No, it's often where you want you can't see it on this because this is the small signal version, so it's not voltages and currents. But right here, same rule as the common emitter. Generally, you like this. If you're doing a general purpose version of this, you have it set between VCC and VCE sat. You kind of pick a resistor. So when you bias this, just like the common emitter, you're setting a current through here. So you set a default current through here, and then you pick a resistor such that V out sits in the middle of the active region of your transistor. Did that work?
So it has less to do with like trying to achieve a certain R out or a certain gain.
If your boss asks you for a particular gain, then you might, if you noticed in the last homework, the current actually dropped out when you used an active load. Current really didn't matter. Let's see how to say this better. So if your boss asks you for a certain gain, you might end up with a resistor that doesn't have V out sitting right in the middle. That was one of the last homework problems where it said, oh, don't make it general purpose, just make it so it has this gain. And then, so the previous homework you set R, you set a default current and then you picked R, so V out would sit kind of in the middle of that legal range. But then the last homework said, we don't care where V out sits at rest, just make it so it has a particular gain.
Okay, so it's essentially like determining where on that VTC essentially it's lying.
Yes.
Okay. Okay.
And it comes out of the specifications most times.
Right. Okay. And then we're not really worried about the R out value then, because we essentially cascade this with something with very low R out, right?
Exactly. Yeah. This thing gets a pass on its R out because we have something that can fix it.
Got it. Okay. Thank you.
Any other questions?
I had a question about the homework.
Okay.
For number 4, it says to do at least 8 small signal analysis using like the single transistor amplifier types.
Yes.
So what do you want us to do for that exactly? Do you want to, like, I wasn't really sure.
Oh, you don't have to turn anything in, just more practice.
Okay.
Yeah.
So,
yeah.
So
like
would it be kind of like what we're doing in class, just finding the different values for different types of amplifiers?
Yes, like finding the R out for common base like we did today, or the R in for common emitter. Yeah, all those just, and then there's the MOSFET MOSFET circuits in there too. So
Okay.
do a few of those too.
Okay, so that's just for practice. There's no turn in for that question.
Yeah, I'll send out an email right now. Make it clear. Thank you.
Okay. All right. Thank you.
Am I still sharing? Oh, I still am sharing.
Yeah.
I have 70,000 unread messages. I don't think that's good. You get to read all my emails. That sounds snarky. Does that sound snarky?
No, I don't think so.
I've asked him like 10 times and he hasn't replied, so.
Oh, you could maybe make it a little snarkier then, really.
Okay.
Like, please, I would really, really appreciate. No, maybe not 2 reallys. That's a lot. No, it's good.
Yeah, I'd keep it
I
like
would-
that.
I always, on my emails, I go too far and then I back up. So my really got lowercase. Okay, sounds good. Okay, I forgot to email that. Any other questions on the homework? Oh, sorry, go ahead.
Yeah, I had another question for part B of number 3.
Okay.
So we got an equation for R out that boiled down to little RO of the PNP and for the NPN.
Okay, in parallel, right?
Yeah.
Yep, perfect.
And so for calculating the little RO, are we supposed to use the early voltage over the current IC?
Exactly.
Okay. So are the early voltages the same for PNP and for NPN?
You have to go to the model file. And for the 750, the early voltage is 70.
Okay.
But for this 650, the early voltage is 100.
Okay, got it. And then is the current going to be 1 milliamp?
Yes.
Okay, awesome. Thank you.
Any other questions on the homework? Ross is still with us. Okay, I think it's 10 after.
Yeah, I think that was all mine.
Okay.
All right.
Oh, is that
thank you.
Russ? Is that Russ speaking?
Yeah.
Oh, okay.
Yeah, those are my questions. Thank you.
Okay, you're welcome to stay another hour.
Okay, I appreciate it, but I think I'm gonna head out.
Okay.
All right, thank you.
Bye-bye. Okay, so let's see. Anything else? I don't think there's any business today. Okay, let's see. So for practice, we're going to look at a different circuit today. Okay, what's that called? Or I'm not sharing, am I? Nope, it says I'm sharing.
What is that on the left side?
Oh.
Sorry.
That's it.
Does that say V bias?
Yes, V bias.
Okay.
So what kind of amplifier is that?
Common base.
Common base. So common base. Okay, so in a lot of books, you see this drawn differently, and I'll show you why in a minute, but let me draw another circuit. What's that?
Common emitter.
Common emitter. So these look a lot alike the way I drew them. Let's look at a few things about them. Let's say I increase V bias, not V bias, sorry, V in. Let's say I increase V in. What happens to the current through the transistor?
Goes up.
Goes up. So goes up. And whatever current goes through the transistor, it also goes through the resistor. So what happens to V out?
It goes down.
Goes down. So let's see if I can get this. Yeah. So V out goes down. So when V in goes up, V out goes down. So what kind of amplifier is this? That's kind of a fuzzy question, but
An inverting amplifier.
inverting amplifier. So common emitter is inverting. Okay. And let's go over here now. And let's say I have V in go up, just like I did over here. I made V in go up. What happens to the current?
It goes down.
Goes down. Why is that?
Because you're decreasing your VBE value.
Exactly.
Therefore, in the IC equation.
Yeah. So both of these circuits change VBE. One holds the emitter constant and changes the base. The other holds the base constant and changes the emitter. So they're really the same circuit. They're both changing VBE. Okay, so let's see. So if the current goes down, what happens to V out?
Goes up.
Goes up. There's less current through the resistor, so there's a smaller voltage drop across the resistor, and V out goes up. So in this case, V in goes up, V out goes up. So what's the common base?
Non-inverting.
Non-inverting. So when the input and the output go the same direction, then it's non-inverting. So that's a big difference between these two. Let's do a slight touchy-feely, not really. If I changed V in by a certain amount, how much does IB change?
Hardly any at all.
Hardly any at all. That's your IC gets divided by beta, and if beta is 100 or 200 or something, IB doesn't change all that much. What about here? If I change V in, what happens to the current there? Does it change a lot or a little?
A lot.
A lot. So this changes a lot. So lot. Whoops. Lot.
Sorry, that's for IB.
That's wherever your V in is. We're looking at the current
okay.
at V in. So I'm sorry. Yeah.
No worries. That makes sense. Thank you.
Okay. So over here, I change V in, and the current changes a little. Does this look like a big resistor or small resistor?
Big resistor.
Big resistor. So the common emitter has a big R in. Okay, over here, I changed V in, and the current changed a lot. So at the input. So what's R in look like there?
Small resistor.
Small. Yes. So that's the other big difference here. So really, the circuits are the same. When you change V in, you're changing VBE. But one is inverting, one's not inverting. And one has a high RN and one has a low RN. Okay. Do you like low RNs?
No.
No, exactly. So there's really only one place that you commonly see a common base used. And let's reach into your memory here. Do you remember the maximum power transfer theorem? Oh, I see somebody nodding. I see one person nodding. Anybody remember that? How do you transfer maximum power?
Maximum current? I don't know.
You'd think, but then it's this. Have you ever worked with or looked at the equations for a solar panel?
Yes. Oh, yes, I do know maximum power transfer. It's when V and I are at their peak values, like along like a V over I chart, or V over I.
Yeah. So when IV's maximum, that's when you're getting your maximum power. And if you go back a long way, that happens when you're connecting two things. If you're connecting two things, if the impedance of the two things are equal, that's when you get your maximum power transfer. So max power transfer theorem, your Z out equals your Z in. I should get rid of those lines because they're weird. Okay, so those are gone. Okay, so the most common place you see a common base is where you have to match impedance. So if it's transmission line or something, or most commonly you see this. That's my symbol for an antenna. You see this. Actually, let me draw it this way. So when you're trying to get a signal off of an antenna, this allows you to match impedance with the antenna and get your maximum power transfer. But otherwise, if you're connecting it up to one of these, like the base here, that's a really high impedance, and you're off the maximum power transfer point. But this you can actually adjust by changing the current. You can adjust what impedance is seen on this emitter, and you can match it to your antenna. Okay, so this is the place where you most see it, and you say, well, wait a minute, this circuit doesn't look like, where is it? It doesn't look like this circuit, but it actually is with the transistor just kind of rotated up. So it can attach to the antenna. So if you took this transistor and just rotated it down below the resistor, it would look like your common emitter, kind of, with the input and the DC switched. Okay, and that's why I think in textbooks they often draw it this way, with the transistor kind of sitting off to the side, because it's often used to receive a signal off of a, again, transmission line or antenna. Okay. But it's not very good because it has such a small RN. If you use it with almost any other circuit, it's going to load that other circuit like mad, and it won't work very well. Okay. So let's analyze this circuit a little bit. This is, actually I didn't try going directly to V in over V out, but it's starting to get a little bit complicated. It's a little more complicated than the common emitter. So to find gain here, I ask you to go through multiple steps. The first one is find GM for circuit. And then find R out is the next step. And then when you find GM and R out, how do you find gain?
GM times R out.
Exactly. So, and then you can find AV by taking GM and multiplying it by your R out. So those are the steps I want you to go through. How about giving, and again, I know you guys are going to be faster, but it's a pretty big room. I think we've got 9 people. Do you want to split up into rooms, or do you want to just work it out here? What's your preference? You know, all of these. Oh, let me say one more thing. Again, is that again, the design process is your boss brings you some specifications. It says gain is 100, RN is 25, something like that. And what you need to do is, since your boss gave you a value for, what did I say, RN and gain, then you need to find the equations for RN and gain for whatever circuit you've picked. To find those equations, you have to do small signal analysis. So what we're doing here is, after your boss gave you specifications, say your boss said, hey, the gain has to be this. Now you have to find the gain equation for whatever circuit you're planning on using, and let's say it's a common base. And so pretend I'm your boss, I gave you a value for gain, now you need to find the equation for gain. And then you set the value that your boss gave you equal to that equation, and then you solve for the unknowns in the equation that you found using small signal analysis. Are those steps okay? Because those are the one of the big items for the quarter. Okay, nodding. Okay. What do you want to do with the breakout rooms? No? Okay.
I know what the best thing to do is.
Yeah, the best thing to do would be in person, but yeah, lots of conversations going on about that. My feeling is that it's just going to be online, even though there's a lot of people fighting for in-person labs next quarter. It's just like even if one person dies, it's too many. And one student already died, but that was because of a false negative. Well, not because of that, but they apparently like looked at the test, said, "Oh no, you don't have COVID. Go home." But okay, so you're a design team of 9 people, and you want everybody on the design team to understand every step you do. What do you think? How about 2 breakout rooms? Just because there's 9 people. Okay, and your goal is to find GM first, and then come back in, say 5 minutes. And should I set it up randomly, or do you want to? I think I had message.
Could you put Tristan and I in the same room so that our voices aren't competing if we're in separate breakout rooms? If that makes sense.
Not really, but.
Well, we're in the same room, so.
Oh, you're in the same room.
Yeah.
In the same physical room?
Yeah.
Cool.
Yeah.
That's nice. That must be nice for labs and everything, huh?
That's pretty helpful. Yeah.
It's all right.
It's just hard
to live with.
Yeah. How are labs going?
They're really time consuming.
It's not the worst though. It is kind of nice because you're not rushed to do it in 3 hours. So you're not like sitting there trying to I feel like I can sit down and understand it rather than just speed through and get the data and be out of there, if that makes sense. So I think that is kind of a nice aspect, but.
Yeah, it's my labs are going to be, well, this week's is okay. And then next week's is going to be a little bit hard. And then then it's just putting stuff together. And that's pretty much the end of my course. We're going to do some simulations after that.
Yeah, definitely. Cool.
Okay.
Cool. Well, I'm going to join my room.
Okay. Hi, my beautifuls. Hi, my beautifuls.
Hello, Professor.
Uh-huh.
I have a quick question. I was just wanted to double check what specs we were given.
For right now, say your boss asked you for gain and you realize this was a complicated circuit. So the first step would be find big GM. So we're not finding,
Okay,
excuse me, a numerical answer.
Okay, cool. Thank you.
Have company?
Yeah.
Oh, your room's back. So. Okay. There we go. Okay, so I'm gonna go kind of step by step to give you an opportunity to ask questions. But first step is always take your circuit, replace the transistor with your small signal model. So that's good for everybody? Okay. Then what we're trying to find first is GM, transconductance, and that's I out over V in. But the reason why when we're trying to find gain, we find big GM is because it GM lets us simplify the circuit. So what's that simplification?
V out equals 0.
V out equals 0. Okay, so I can leave that. So I can set V out equal to 0. What else do I get to simplify here?
The current source goes to resistor of 1 over GM.
Okay, but before that, what happens to that?
Oh, that goes to the ground, sorry.
Yeah, and then what you just said. So, okay, so I always like to write in VBE because when resistors start to be put in parallel and all that, I lose track of where VBE is. So I just put that in as a note. So now we've got this. Anything else? So you said this can go away, or does it go away completely?
It goes to resistor of size 1 over GM.
Yes, okay. So this node, the way to see whether this goes to a resistor of size 1 over GM is to see if your base and your collector have the same voltage. Does the base and the collector have the same voltage?
Yes.
Yes. And the emitter, the emitter is, I mean, they both tied to the emitter, so the other side always has the same voltage. So if the base and the collector have the same voltage, then this gets to go to a resistor. What happens to this resistor?
Goes away.
Goes away. So that goes away. This turns into a resistor of size 1 over GM. That's rule number 4. This is V in. This is V out. And for GM, you're looking at I out. And so I out is the current out of the output. So so I out, you're looking for I out over V in. Let's go step by step. So this I out, V equals IR, so V in equals I out times, these two resistors are in parallel. But what you want is I out over V in. So you get I out over V in, which you know equals GM, equals 1 over RO parallel 1 over GM. And it actually comes out kind of nice. It comes out to GM plus 1 over RO. If you work it out. And what's 1 over RO?
Really, really small.
Really, really small. So this is usually approximated as, as just GM.
I'm sorry. Why did you get rid of R pi?
Okay. So what we're looking for is the current out of the output. This right here, this is the base right here. So this current isn't going out the output, it's going in the base of the transistor or out the base of the transistor. But we're looking at the collector, the current coming off of the collector. I know both of these are ground, so it seems like the current's going to the same place. It's just not going through the collector to get to ground over here, so it's not included in I out.
Okay, that makes sense.
Okay. So, all right, so we've got half of our gain equation. Your next challenge is to, so any questions on that? Yep, and why we're finding these equations? Okay. We're assuming the boss asked us to make a common base amplifier. Probably wouldn't say that. Probably say we're trying to make an amplifier that connects to an antenna, and it has to have a gain of at least something. So we're trying to find the equation for gain to set equal to whatever the boss said it has to equal. Okay, so next step is what? If you're finding gain?
Find R out.
Find R out. So go ahead and find R out in your groups. And how about like 6 minutes? I'd say 5 minutes. I bet you can do this one in 5. Here, okay. Did that solution look familiar?
Yes.
Yes. Okay. They're starting to come back. Was that a full 5 minutes? I forgot to check. Only one person's back from the other room. Should I go pop in and say, come on back? Hi. Y'all want to come on back?
Yeah.
Okay. I saw a thing, this has nothing to do with the E308, but I saw a thing on someplace about how many doctors there are serving the Navajo Nation, and there's really just one at the emergency place, and tell you, it's rough out there. Is everyone back? I think, oh, the breakout room disappeared, so I think that means yes. Yep. Okay. All right. So, again, reason why we're finding GM and R out separately is because you get to make the circuit simpler, so you can do analysis. What's the simplification you can do for R out? Okay. I can
V in 0.
Vn equals 0. So let's do that, and I'll try not to forget that VB is whoops. Oh, that's kind of pretty. Okay, I think I got it now.
Oh, you're not sharing, I don't think.
I'm not sharing.
I think it canceled it when you went to the breakout room.
Okay. I'll make that my excuse. Okay. All right, so VB is grounded, and then for R out, you also get to ground V in. Okay, so anything we can get rid of?
R pi.
R pi, and why can you get rid of R pi?
0 volts on both sides.
0 volts on both sides. So R pi goes away.
Can you
What
also
else?
get rid of the current source as well?
Yes, and why can you get rid of the current source?
VBE, which is the same as the voltage across.
Exactly. So VBE is 0, 0 times anything is 0, so that goes away. And then all you're left with is R and RO. Can you prettify that? So I can't hear anybody, but I think I saw 2 people say put them in parallel. So what happens is get RO parallel R. And if someone had a resistor, like we did in one of the earlier workshops, they said worksheets, find the value of this resistor. You'd put a voltage on here, and you'd watch the current going into the black box. So when you're finding R out, you don't use I out. You don't use the current going in that direction. You're looking at this whole thing. You're looking at this whole thing as a mystery box, and you're trying to figure out how big a resistance this looks like. So you actually put I into your circuit, just like you did here. You put I into the black box to try to figure out what the resistor is. And so I wanted to give it a different name than I out, so I just call it I test. And in this case, it's pretty straightforward what R out would be, since it's just a resistor. But when we get to more complicated circuits, this using I test is going to be important. So even though it's pretty straightforward, I'm going to write it in here. It should be lowercase, sorry. I test. And then I'd set up an equation. I know V equals IR, so I have V out equals I test RO parallel R. And then I know that for R out, I want V out over I test, so I would divide both sides by I test, and I get RO parallel R. Okay, so these, if it was a more complicated circuits, this would be kind of your steps you would go through. You'd need to use that I test, put it into the circuit, and see how much the voltage changes. Okay, so let's kind of summarize. We've got big GM equals to GM. Got R out. We just found R out. R plus R. And what's your gain?
GM times RO in parallel with R.
GM RO parallel with R. And does that look familiar?
That's common emitter gain, except positive.
Yes, exactly. So when we saw up above, when we did kind of the touchy-feely version, we saw that the common base was non-inverting. So you get a positive gain here. But when you did the analysis of the gain of the common emitter, you saw doing the touchy-feely that it's inverting, and you got a minus sign. So the GM is actually where, whether it's inverting or non-inverting, that's where it shows up by the sign in front of GM. Okay. There's something else I said. Oh, okay. So it's interesting that you get the same gain for the common base and the common emitter, but if you go back and look at the original circuits, they're exactly the same. They're both just changing VBE. One changes VBE by holding the emitter constant and moving the base. The other one holds the base constant and moves the emitter, but they're both changing VBE, so it's not too strange that their gains equal each other. And on the last homework, you should have found a gain pretty close for the common base and the common emitter. But what's the big difference between the two? Or two big differences?
One's negative and one's positive.
One's inverting, one's not inverting.
And then Rn is really low for common base and really high for common emitter.
Yes, so it's the difference in the RNs and whether it's inverting or not inverting. So actually, putting you into breakout rooms got us pretty close to the same time as the other class. Let's see. Rn is, just a second, Rn would be, don't get to simplify anything. I'm gonna, just since we have 5 minutes left, I mentioned last time that after doing all this math, and we'll do 2 more days of this math, and then next Friday we'll see how to get all these values without doing math, and then you'll hate me because we just did a week and a half of math. But when for a common base, the Rn is approximately 1 over GM. And for any of you that have worked with antennas, do you remember impedance of transit of antennas? Like at the connector? There's usually two values you see. Sometimes you see a 50 ohm, sometimes you see a 75 ohm. And you've probably seen that in other devices too, where they have a 75 ohm or a 50 ohm output impedance. So let's say your boss says, oh, I've got a 50 ohm impedance at the frequency I'm interested in. I have a 50 ohm Z out equals 50 ohms. And now I'm going to connect it to a common base, but I want to have maximum power transfer. And I know my Rin equals 1 over GM. How do I get maximum power transfer?
One over GM should equal 50.
Exactly. And you remember that, do you remember what GM is?
IC over VA, I think.
IC over
VT.
Yes. Okay, so 1 over GM, you have VT over IC equals 50 ohms. And now you just have whatever your VT is divided by 50 ohms equals your IC. And so you can design so you get the maximum power transfer at whatever impedance, whatever frequency gives you that 50 ohm impedance. Make that a little bit prettier. And that's where this might be used. Okay. That's all I have. I can keep talking. You know me. But so have you heard of low noise amplifiers? So when a signal gets transmitted, so let's say this is a radio station. When it gets transmitted, it might start out like this, but by the time it gets to the receiver, it's very small. And you have to amplify it up. But there's probably been some noise added. So if you just amplify this up to the regular size, lots of times that noise also gets amplified and you're in trouble. But when you get it, it's so small, you can't really work with it. You can't just filter it out because the amplitude is so small. If you filter it, you lose your actual signal too. So what you often have is a low noise amplifier. And they are made to introduce as little noise as possible. So they receive this very small signal that has some noise on it. You want to filter out the noise, but if you filter it out just right off the antenna, you kill your actual signal too. So you need to amplify it up, and this could be, a gain of 5 or a gain of 10, just enough so that when you put it through your filter, you'll still get your signal. And then you put it through a filter. Usually, well, whatever kind of filter you need. But a lot of times these low noise amplifiers are implemented with a common base or a common gate. Okay. Next week, I'm actually throwing something at you in the homework so we can maybe build something like a radio in LT Spice. So it's not all that exciting, but okay, that's all I got.
Bye. Thank you.
All right, bye. If there's any questions, feel free to stay on.
Enjoy your weekend.
No, thank you. You too.
We have some questions about the homework.
Absolutely. I thought that might be why you were joining us.
Yep.
Yeah.
Okay. Let me save this just to make sure I don't accidentally delete it. Oh, I should stop recording.
Okay.